Hey everybody, we're going to be talking about half-life and half-life calculations today. And this is exponential decay, which you may have seen in your algebra classes, but for our purposes in chemistry here, we're going to be using a similar equation that might help you in algebra, so there you go. All right, the usual form of an exponential decay equation is y equals ce to the kt. And we need to know what things are in this equation. So if we're dealing with amounts of radioactive atoms before and after and the half-life, here's what each variable stands for. Y is equal to the final amount. Now, amounts can be measured a lot of different ways, but it's going to be the amount at the end after it decays. That's what we're talking about when we're talking about Y. C is the initial amount. This is your starting amount of however many radioactive atoms you have. Now, sometimes you might not be given initial amounts. If you're working with fractions, you can assume that the initial amount is the whole fraction, or 1. So C would be 1 if you ever see problems where it's giving you, or it's asking you for, what fraction remains after it decays for so long. If you're working with percentages, then C is probably going to be 100 because you're starting with the whole percentage or the whole amount before it decays, and that whole amount as a percentage would be 100. K in this equation is a rate constant. Now, you're probably not going to see too many half-life problems that are going to give you a rate constant. Most of the time they give you a half-life. This K is probably something that we're going to have to get for ourselves if we're going to use this equation. We'll be able to get it from a half-life using this other equation here. T in this equation is the time of decay, so that's how long it's going to decay, the whole amount of time that it's decaying from the final amount, or from the initial amount to the final amount. And T 1/2, now this little 1/2 is not actually math, this is just a label to show the difference between these two T's. This is the whole amount of time of decay, and this is the half-life for whatever isotope that you happen to be working with. So a whole lot of problems are going to ask you for a final amount. So that's probably the number one kind of problem that you would see using these equations. And the way to go about it usually is if it gives you a half-life for a certain radioactive isotope, then you can plug that half-life into the bottom of this equation and divide these two numbers to get a K that you can then use in this other equation. Okay, the top of this equation, this negative 0.693, is actually the natural log of 1/2, but just in case you're not familiar with logarithms, we're going to go with this version of the equation. Okay, all right, so let's do a few examples to see how we're doing here. And we'll switch over to this thing with my examples on it. Okay, so there's a few example problems, and we'll pull up my handy-dandy calculator to use right over here. Okay. All right, so in the first example here, this says radium-223 has a half-life of 12 days. What percentage of radium-223 will be left after it decays for 36 days? The first thing I want to point out when you're looking at a problem like this is there's a number in here that isn't important. Okay, you got a bunch of numbers in this question. Which number isn't important? If you said this 223, you were right. Okay, that is the mass number of that isotope, but mass number is not used in these calculations. That's just telling you which isotope we're talking about of radium. So we're not going to use that 223, but we need to identify these other things. So we've got a 12 days here, and we've got a 36 days. And I always like to label my variables, and it helps me organize my thoughts. Well, this one says radium has a half-life of this. So which variable in these equations is this 12 days? Well, this 12 days is the half-life. Okay, so this guy is equal to the T 1/2 that's in this equation. This 36 days is apparently how long it's decaying. It wants to know what percentage will be left after it decays for this 36 days. So this is going to be equal to the time. Okay. All right, and you may be looking at this equation being like, okay, I need to find how much is left, I need to find my Y, but I still have missing information in this equation. What the heck is C and what is E? Well, C is not given to you here, but it's asking for percentages. So C is probably going to be 100% since we're working with percentages, okay? Now remember, the E is a constant. It's in your calculator, actually. If you hit the second divide symbol on most TI calculators, it'll give you E's. Kind of like pi. Pi is 3.14, E is 2.7 something, but you can just get that E value from your calculator. Okay, all right, looks like we got everything that we need to go ahead and try to find the Y here, and really there's not a whole lot that we need to do here, so we'll go ahead and go to the calculator then. So Y would be equal to CE raised to the KT power. I know if I'm working with percentages that C is 100, so we'll go ahead and put in 100. Times E. Okay, so the E is, again, usually on most scientific calculators right above the divide symbol there. So that's your E. Now we're going to raise those to a power. Now, if you have a calculator that actually lifts the numbers up, then you don't have to do what I'm getting ready to show you. But if you have an older model calculator that uses this caret symbol and keeps everything down here, it might be a good idea to put parentheses around these two things, because we're going to be multiplying two numbers together that are both in the exponents. And so I'm going to go ahead and multiply together my K and my T. Now, I hit a stopping point here. I don't know what the K is yet, so I'm going to have to go back to this other equation for a second. Okay, so let's go back to the other equation. K is equal to the negative 0.693 divided by the half-life, and the half-life is, in this problem, 12 days. And there we go. So there's my K. Now, so that you don't have to retype that, a nice feature on most calculators is a store function, or you can use the second answer key as well if you wanted to, but I like the store function. Hit this little STO button right after you get that answer for your K, and it'll take that answer and give you an arrow, and then if you come up here, you can hit the variable button, and it'll stick an X in here, and then if you just hit enter, it'll store that number as X. So anytime you go back here and hit X, now you've got that number over and over again. So we've got our K value that we don't have to retype. That's a feature that can really make these problems go a whole lot easier. All right, so now I have a K. So let's go back to this other equation. Y equals CE to the KT. Again, Y equals C, which is 100. So I plugged in 100 for C, times E. And then we're going to raise that to the power of K and T multiplied together. Now, the K was the number I just got. I could retype that in there if I wanted to, but I'm going to use the X function that I just stored that number to X to make it a little bit easier. And then times the T, which is the total amount of time, times the 36 days. Okay. All right, and I'm going to round this number off. So the final amount, the Y in this problem, was equal to 12.5%. Okay, final answer, 12.5%. Now, let's use some common sense for a second. If you started with 100% and the half-life is 12 days, after 12 days, how much would be left? Well, again, the half-life is the amount of time it takes for half of what you started with to decay. So half of what I started with would be 50%. That's after 12 days. What about after another 12 days? Well, it's going to get cut in half again from 50 to 25%. And how about another 12 days? 25 would get cut in half to half of 12.5 is, or half of 25 is 12.5%, which is what we ended up with. This is a total of 36 days. 36 days happen to be equal to 3 half-lives. And because there were 3 half-lives, our original starting amount got cut in half 3 times. So there you go. Okay? All right, let's try the second example here. In the second example, it says, if only 5 grams of radium-223 remain after 90 days of decay, how much was in the original sample? Okay, so this time, if it's asking me for how much was in the original sample, which variable is it asking me for? Well, remember, the original amount, the initial amount is c. So this wants to know what c is in the equation. Now, if you take this equation and solve it for c, c would be equal to y over, imagine this e to the kt thing is all one number. To get c by itself, you'd have to divide this to the other side. So y over ce, over just the e to the kt. All right, now I'm not going to make the same mistake I did last time. I didn't have a k value. But you know what? This radium-223 is still the same isotope I had in the previous example. So the K that I got by taking the negative 0.693 and dividing it by the half-life, it's the same K, and I still have that K stored in my calculator as X. That's what I got when I took the negative 0.693 and divided it by the half-life of 12 days there. Okay? All right, so I'm going to get C by taking the Y and dividing it by e to the kt. This is the final amount. This is my Y. Now, to prevent any problems here, I'm going to do this problem in 2 steps. There's a lot of stuff in the bottom here. I'm going to go ahead and get a number for the bottom, and then I'm just going to take the Y and divide it by the answer that I just got. Okay, so let's focus in on the bottom here just for a second, this e to the kt. So if I go ahead and just get the bottom by doing e raised to the power of k times the total amount of time, total time of decay in this problem is 90 days times 90, that's going to give me just the bottom of that fraction. Okay, so that's the bottom. Now, the answer will be y divided by e to the kt. Well, that's e to the kt. I just got it. So all I'm going to do is take 5 and divide by the answer that I just got for e to the kt. I'm going to use the second answer function, second answer, and get my answer. Okay? So, you know, you'd expect to get an amount that's larger than 5 grams here because this thing is decaying and 5 grams is left at the end, which means we must have started with way more than 5 grams at the beginning. So our initial starting amount looks like it was about 904 grams in this problem. Okay? All right. In the next problem here, I'm going to skip the equations for a second and go to some common sense. Okay? The reason I'm going to do that is because I see 12 days is going to fit into 48 days an even number of time. This is my half-life in this problem. This is t1 half, and this 48 days is the total amount of time. That's the t. Okay? If the half-life will fit into the total amount of time, a whole number, an even number of times, then you're not really going to need to use these equations. You really could use common sense because you know every half-life that passes, your starting amount is going to get cut in half. Now, this is asking what fraction. If we're working with fractions, what's our starting amount? Well, the starting amount is 1. So if I start with 1, I'm going to cut it in half to 1/2 after 12 days. After another 12 days, a half is going to get cut in half. What's a half of a half? A fourth. After another 12 days, it's going to get cut in half to an eighth. All right, that's 36 days. After another 12 days, that's going to make 12 and 12 and 12 and 12 makes 48. Then an eighth would get cut in half to 1/16. So apparently 1/16 of our starting amount would remain. Okay? All right, I'm going to leave the last example problem to you. Those are some examples to help you guys solve half-life problems using exponential decay half-life equations or maybe using common sense.